We are going to look at components of a topological space. So to understand how these look like, we are going to first induce a notion of what? We are going to first define an equivalence relation. To understand these components of a topological space, we're going to first obtain some tools. So we are going to let X be a topological space. Let X be a topological space X. Let X and Y be in X. Then X is related to Y. We are going to define an equivalence relation on X. We are going to define an equivalence relation on X. So define, we are going to define an equivalence relation on X as follows. X is related to Y if there exists a connected subspace. X is related to Y if there exists a connected subspace of X. Related to Y if there exists a connected subspace of X containing X and Y. Now what next? We have to convince ourselves that that is actually an equivalence relation. So proof. What are we proving? We are proving that this relation is an equivalence relation on X, on elements of X, the equivalence relation. Reflexivity. So an equivalence relation, you have to prove that it's reflexive, transitive, and symmetric. So for reflexivity, we have to show that X is related to Y. So we show that let X be in X. Then we show that X is related to X. That's what we have to show. As in, we show that there exists a connected subspace of X containing X. So let X be in X, then define W to be a singleton, to be that set. Then, since W is containing a single element, then W is connected. is a connected subspace. W is connected subspace of X containing X. So this implies that X is related to X. Now, symmetry. We are going to let X be elements, X and Y be elements of X. Now suppose that X is related to Y. This implies that there exists a connected subspace. There exists a connected subspace T of X, there exists a connected subspace T of X containing X and Y. Now you realize that, observe that T is a connected subspace, the connected subspace of X containing Y and X, implying that Y is related to X. Implying that Y is related to X. Implying that Y is related to X. So we have another property, reflexive symmetry and transitivity. So we are going to let X, Y, and Z be elements of capital X. Now suppose that X is related to Y and Y is related to Z. So this implies that there exists connected subspaces. There exist connected subspaces. W and Y. There exist connected subspaces W and Y of X. There exist connected subspaces W and Y of X such that remember, X is related to Y if there exists a connected subspace of X containing X and Y. So X is related to Y, there exists connected subspaces W, Y is related to Z, there exists connected subspace Y such that W contains X and Y, and Y contains what? And Y contains Y and Z. Let me first see this. There exists connected subspaces W and Y of X such that W contains X and Y contains Y and Z. So what does this imply? You observe that so this implies that X and Y are in W and Y and Z are in Y. Then Y is in W and Y is also in capital Y. So Y is in W intersection Y. Y is in W intersection Y. Now we have connected subspaces. You have to recall the previous results. We have connected subspaces W and Y having a point in common. We have connected subspaces W and Y having a point in common. So this implies that by the previous results, connected subspaces of a topological space having a point in common. For connected subspaces of a topological space having a point in common, their union is connected. So this implies that W union Y is connected How have we been able to conclude that it is connected? By the previous results. We prove that the union of connected subspaces of a topological space having point in common is connected. So this implies that W, since W and Y have a point in common, then W union Y is connected. Hence, and since X is in W union Y, then also Y now is in W union Y. So this implies that W union Y is a connected subspace. The connected subspace of X is a connected subspace of X containing X and containing X and what? Containing X and let me first see this thing. Containing X and no. Actually, I have to show that X is related to Z. X is related to Z. So let me first check some things. So X is in W. We have been able to conclude that W union Y is connected. So X is in W union Y and Z. Remember Z was in Y. So X is in W union Y and Z is also in this union. So we can conclude that W union Y is a connected subspace of X containing X and Z, implying that X is related to Z. So that relation is actually an equivalence relation. Is an equivalence relation, and we can now talk about equivalence classes. Now the relation defined before, that relation, how did we define that relation? We say that X is related to Y if there exists a connected subspace of X containing X and Y. So the relation defined before induces equivalence classes known as components. Induces equivalence classes known as components. So let us define definition of a component. So we are going to let X be a topological space. Let X be a topological space. Then a subset of X. Let X be a topological space. A subset of X, comma, a connected. X is a topological space. We are having A as a subset of X. Then that A, assuming that A is connected, comma, then A is a component. A is a component of X. A is a component of X if there is no connected subspace, if there is no connected subspace of X containing containing A. If there is no connected subspace of X containing A. So X is a topological space. We are letting A to be a subset of X such that A is connected. Then A is called a component. A is called a component of X if there exists no connected subspace of X containing A. In other words, A is the maximal connected subspace of X. Why is it maximal? Because if it's a component, then there must exist no connected subspace of X containing A. So we shouldn't have a connected subspace such that space contains A. In other words, that implies that A now becomes the maximal connected subspace of a topological space X.